Alright, in this video we're going to do an example that involves impedance reflection, and this example actually mimics a very popular practical situation where we've got some impedance ZS, and you can see here that in this problem ZS is equal to 3.1 minus J 1.78 ohms, and we have a ZL that we're given the real part 7. So right away you can see that we can't make a match between ZL and ZS directly, since the real parts aren't even the same. But also ZL, the imaginary part, is unknown. Alright, so this is a variable that we can have some control over as far as in our design. Okay, so the imaginary part of that load impedance is unknown, and this is very practical because in lots of practical situations, whatever you have on the primary side of a transformer, like your main circuit, well, you're pretty much stuck with what that impedance is, because to try to change ZS in a real world type of situation like this would require a lot of effort, where typically the load, what's being driven by the transformer, you have much more flexibility. You don't have total flexibility, and that's why one component of the impedance here is fixed, just to represent that there isn't maximum flexibility, but there is some flexibility in the design here where we can control what the imaginary part is, the reactive part of the load. And then the other variable here is the turns ratio N of the transformer. See, that's something we have total control over. You can get a transformer of any turns ratio you want. It's just a matter of getting the right ratio between these turns on each side of our iron core, which is very easy to do. So there's loads of flexibility with the turns ratio. So the fact that that's an unknown in this problem represents that maximum flexibility. Well, remember, with a transformer, to get maximum power transfer, we want RL to equal N squared RS. Okay, that's a squared there. And also we need the reactance of the load to be minus N squared XS. So we can solve for N, right? N squared, since we know, see, because this is RS right here, and RL is 7. So using these values, what we're going to have RL, which is 7, divided by RS, which is 3.1. Right, get rid of the squared by square rooting this. So the turns ratio, 7 over 3.1 square rooted, will give us an answer of 1.5. So 1.5. So that just means that for every 3 turns on the secondary side, we have 2 turns on the primary side. So we found what the turns ratio is. Now we can get what this unknown reactive part of the load is. That's XL. Okay, so XL is going to be minus 1.5 squared. Okay, now here you have to be careful. Now, we know that we need a complex conjugate, so since we got a minus here for the imaginary part of ZS, we know that the imaginary part of the load has to be positive. So for that reason, when you put in XS, include the minus sign. So you see we include minus with the 1.78. Alright, and if you multiply that out, you'll see that you get 4. Okay, so that's what B is equal to. Alright, so we now know the 2 unknowns, right? Turns ratio 1.5, and then the imaginary part here, B of ZL, 4. Now the last thing we're going to do is actually calculate the amount of power delivered to the impedance load. So to do that, alright, so this is to define P average, because remember that's the power that gets maximized when we're maximizing power in an AC circuit to an impedance. So to find P average of ZL, this is where you use your equivalent circuit, at least to start, you use your equivalent circuit from primary perspective. Okay, so we're going to have our source 10 at an angle of 0 degrees, and here's our ZS, the 3.1 minus J 1.78. Okay, now remember, what goes in here is ZL over N squared. Well, if we did this correctly, and we came up with 7 plus J4 over 1.5 squared. Well, if we did this correctly, when we work this out, we should get the complex conjugate of ZS, because after all, that's what we designed for. So you see this will come out to 3.1 plus J 1.78. Okay, so now if we find the current flowing in this loop, that's our primary current. Okay, so yeah, this here, we'll just write this in. Okay, so now I1 is just going to be the source voltage divided by the impedance in this path, and since they're complex conjugates, the imaginary parts cancel out, and we're just left with the real part. 6.2, 3.1 times 2. So that gives us a primary current of 1.61 amps. Okay, but we want to find P average of the load. Okay, so this circuit just gives us primary values. Now we need secondary value for current. And to do that, we use the transformation equation that secondary current is just primary current divided by the turns ratio. So you have 1.61 amps divided by the turns ratio 1.5. Okay, so you're going to see this is slightly over 1. Secondary current comes out to 1.073 amps. Okay, and then the last part is that P average, as we saw in earlier videos, is just I squared R, and this is for the load. So P average would just be I2, because that is the current through the load. Okay, 1.073 squared, and then RL, which is the resistive part of the load, ZL, which is 7, and this comes out to approximately 8 watts, and that's our answer for P average. So that's our answer right there. So when you're doing problems like this, you first find your primary value, the current, then use the source transformation equation, and then I squared R to get P average. Now you could also find the voltage V1. If you wanted to do it a different way, you could find the voltage here, V1, primary voltage, then use the transformation equation for voltage. That would give you the secondary voltage, but you have to remember that that secondary voltage is across the entire impedance, okay, R plus X, so you'd have to use voltage divider just to find the voltage across the resistive part of ZL to get P average. But as long as you do that all correctly, you would end up with the same answer. Okay, well that finishes the last video of the quarter. I hope you had a good quarter, and hope you have fun preparing for the final.